Welcome to the SaberRD online training course. This series of fast-paced videos will teach you the full power of the SaberRD simulation environment. In this section, we explore Monte Carlo analysis. Monte Carlo is a prominent method for determining likely outcomes in the presence of random variations. For system design, it predicts how input variations, manufacturing tolerances, and environmental factors affect performance, making it an essential tool for robust design. SaberRD's Monte Carlo implementation expands the effectiveness of Monte Carlo with flexible statistical modeling, rapid execution, and productive automation. Not only does it predict behavior, but it supplies the tools needed to remedy problems. Let's look at Saber's Monte Carlo implementation. We start with circuit parameters. Typically, we specify component parameters with scalar values, such as 4.7K. Formulae and functions can also define them. When we plan to run Monte Carlo, we incorporate probability distribution functions. The most common one defines normal distributions. There are two ways to define a normal distribution. If there are two arguments, the first one is the nominal value and the second is the tolerance. The tolerance corresponds to the statistical 3 sigma points. If there are 3 arguments to the function, the first is the nominal value, the second is the lower 3 sigma point, and the third is the higher 3 sigma point. Saber provides other, more specialized distribution functions, along with parameter correlation. The Saber user manual describes them in detail. We'll use an example to show how Saber's Monte Carlo improves the robustness of a design. The circuit is an AC to DC converter using an average model for the pulse width modulator. We want the output voltage to remain within 50 millivolts of 12 volts, even in the presence of variances due to component tolerances. Therefore, we want the 3 sigma limits to be less than 50 millivolts. A direct way to access Monte Carlo is by selecting a simulation and changing the looping specification. However, instead of using Monte Carlo in this manner, we'll create a reusable experiment to automate the process. There's a separate Saber training video that introduces experiments. We open the Experiments panel along the right side, click the icon to create a new experiment, and give it the identifier name MC. The Experiment tab is displayed along with a canvas for the experiment's tasks. Clicking the Monte Carlo task puts it on the canvas. We add a transient analysis to the Monte Carlo loop and change the end time to 20 milliseconds. The loop is set to execute 80 times. To cut the simulation time, we set up parallel execution in the Properties section, utilizing the computer's 4 physical cores. We need to specify which signals to plot. Clicking the Define Graph button creates a container for the signals. We change the container's name to Plot versus Time. Pressing the Plot Signal button adds a signal to the container. Clicking on the question mark lets us select the transient plot file and find the DC output voltage in the design hierarchy. We rename the signal Vout. Let's try out our initial Monte Carlo experiment. We go to the Simulation tab, select Experiment from the pull-down, and choose our new experiment. Pressing the green arrow button runs the experiment. After a few seconds, the plots container appears in the results pane. Double-clicking it shows the 80 overlaid Monte Carlo runs for Vout. Now it's time to add measurements to our experiment. We add one after the Monte Carlo loop and choose the output voltage from the transient plot file. We keep the measurement type to the default, which checks the voltage level at the end of the simulation. Because the measurement operates on a family of curves, it will generate a scatter plot. In the Properties pane, we change its name to Vout Scatter 1. Changing the log property to Yes will add it to the experiment's report. We can make statistical measures on the scatter plot. We calculate the mean of the Monte Carlo runs by adding a measurement and selecting the scatter plot as the input waveform. The mean measurement is under the Statistics category. In the Properties pane, we change the log property to Yes and give the measurement a more descriptive name. We create another measurement for calculating the standard deviation. To determine the 3 sigma limits, we add a calculation task and multiply the standard deviation by 3. Changing the log property to Yes will add it to the experiment's report. If the 3 sigma limits are not within the design requirements, we must determine which parameters to change. To assist us, we add another measurement and apply a Pareto analysis to the scatter plot. We need to select the parameters file generated by the Monte Carlo task. In the Properties pane, we change the minimums to 0 so all parameters appear in the chart. We change the log property to yes to generate a link to the Pareto chart in the experiments report and rename the measurement. It's time to execute the experiment again with these additional tasks. An experiment report is created. We see it includes the measurements for the mean and 3 sigma limits and links to the scatter plot and Pareto chart. Let's look at the scatter plot. The x-axis indicates the run number and the y-axis shows the output value. We can create a histogram of the scatter plot by going to the Analyze tab and selecting Apply Measures. We change the measurement to Statistics, Histogram. Before we create the histogram, we select Edit and Measure Preferences. Among the many settings, we can change the number of histogram bins to 10. Hitting Apply and Close get us back to the measurement dialog window. Selecting Apply creates the histogram. Going back to the experiment report, we see the 3 sigma limits exceed our 50 millivolt requirement. We'll use the Pareto diagram to assist us. Clicking on the plot link displays it. The bars correspond to parameters. The ones with the highest magnitude have the most impact on the output voltage variation. It's clear the parameters with the most impact are the reference voltage and resistances of R1 and R2. We want to decrease the tolerances of these 3 parameters and compare their effects to the original circuit. We could make changes directly to the schematic and rerun our experiment. However, we can further leverage automation by adding to our experiment. First, we add 3 alter tasks. The first alter reduces the reference voltage tolerance to 0.05%. The next 2 lower the tolerances of R1 and R2 to 0.1%. We repeat the Monte Carlo, measurement, and calculation tasks. All the results will be put into one experiment report, making them easy to compare. We run the experiment again. The report makes it easy to compare the new results with those of the original circuit. The changes we made put us well within the 50 millivolt 3 sigma requirement. Experiments give us the confidence to explore design trade-offs, knowing that whenever we make a change, experiments thoroughly exercise the circuit, ensuring design integrity. This concludes this section of the SaberRD online training course. To download a free student version of SaberRD, go to the Synopsys website. To further your understanding of this material, go through the lab exercises found at the link listed in the description of this video.